Right. Yeah, I hope that is the case. And I'll be talking about this. My talk today is about artificial intelligence, or if you will, artificial stupidity. And that is not just like a clickbait title that I gave to this talk so that you all join it. There actually is something behind it, and I'll go a little bit deeper into that later. Why I call artificial intelligence artificial stupidity. Right. But in general, what I'll be doing today is I'll be telling you a couple of stories, and these stories, some of them will be success stories. So all of them will be about machine learning and AI and data in a way. And some of them will be success stories about things that in relationship to ML or AI that happened and that went pretty well. But also some of them will be stories about failures, and particularly about these failure ones. I'll dig a little bit deeper into them and see why they failed and how we can prevent these failures to happen in the future again. And when I say I talk about, I tell you about stories. There's this fantastic, one of the greatest storytellers, in my opinion at least, which is Douglas Adams. And I'm relatively sure that some of you have read this book, which is the Hitchhiker's Guide to the Galaxy. And this book has brought us a couple of pretty famous memes nowadays, which is that 42 is the answer to the question of life, the universe, and everything, and that we should not panic. But apart from these memes, Douglas Adams has introduced with this book something else that is not as popular, but especially in this context, at least I find very interesting. And what Douglas Adams has introduced is this so-called Babel fish. And this Babel fish is this fictitious fish that is like tiny and yellow. And how that is used is you can stick this little fish into your ear, and due to it absorbing brain waves and whatnot, it is somehow able to hear all the languages that are spoken, all the words that are spoken around you in any language, and is able to translate that directly into your ear into a language that you understand. And that is, that is obviously it's a fictitious idea. It's a crazy idea. Douglas Adams has a fantastic humor, and that is one way how he thinks it's this crazy thing that obviously in real life could never happen, right? Well, let me show you something else. There's this. I'm gonna try this now. Hallo und herzlich willkommen zu meinem Vortrag über künstliche Intelligenz. Right, and what we see here is that I talked about this fictitious fish that can translate things, right? Due to machine learning, and obviously the machine learning that Google is using here is kind of advanced, right? Or like at least I hope so. At least it looks like it. But due to machine learning, we are nowadays able to almost fulfill these tasks that a couple of decades ago seemed absolutely unimaginable in real life. Like I can just speak in any language more or less, and it translates into real time, in this case, into English. And yes, I had to click this button, and I need a computer, and it's not in my ear right now. But it is already pretty close to this fictitious idea, to this thing that was unimaginable in to be happening in real life. But then there is now I say it's not quite there yet, right? But in fact, it is I mean, there's no, you still have, you need this computer, right? And you can't stick it in your ear. But Google also has these earbuds, right? These are, in fact, tiny little earbuds that you stick into your ear. And they do exactly, more or less, exactly what this Babel Fish does. They listen to the words around you being spoken. And it gets translated. I mean, it gets translated on a phone, and it doesn't directly get translated on the device in your ear. I give it a couple of years, right? And the thing is that that it is in your ear, and it translates into a language that you do understand. So that being said, the idea of this Babel Fish is almost reproduced by technology that is powered by machine learning nowadays. And I think that is a very powerful example. And there are countless other examples where machine learning is actually empowering lots of areas in our daily life. And another example, for example, is how machine learning has been able to predict cancer based on image data, like we can see here, more effectively, more efficiently, with a higher accuracy than humans, like human doctors. Human doctors have like studied that, right, for years and years. And machine learning is nowadays better in looking at this image and deciding whether there are cancer cells or not. And that started a couple of years ago. I think breast cancer was the first type of cancer that was where machine learning algorithms outperformed humans. And I think last year, Google released a model that outperforms lung cancer identification based on image data. And this is a life-changing improvement done by machine learning. So there are absolutely fantastic use cases and absolutely fantastic results that we nowadays already achieve with machine learning. But, and I mentioned it before, the title of this presentation would not be something about artificial stupidity if it always would work as good as these two examples that I gave. And you can here you can see some of the other examples. For example, the person on the right who tweeted to Indigo, which is an Indian airline, that he is thanking this airline for sending his baggage to Hyderabad while flying himself to Calcutta. Now, you as a human probably do understand that this is sarcasm and that he's making fun of it. I assume there's a machine answering, and by reading the text, it's like, oh, the customer is thankful. The tweet from Indigo is, we're glad to hear that. Obviously, that horribly failed trying to understand the intent. In the middle, we can see a chatbot talking to a PayPal customer, which just said, "I got scammed," and the reply is, "Hey, great." So clearly, there are obviously cases where the technology and I imply there's some kind of AI behind this fails, and the left one also is a great example where the understanding of the intent actually failed. And my absolute favorite example for today where machine learning failed horribly is this one. If you speak Mandarin, you can already guess what's going on here. But for everyone else, I give you a little bit context. There are a couple of cities in China where there are pedestrian crossing, like zebra crossings, where a person can cross the street, and there are traffic lights, just like in most other countries. If it's red, then you can't cross the street. If it's green, you can cross. And in these couple of cities in China, what they have set up is a camera system image recognition above the light, and when someone has a red light, some pedestrian has a red light and is crossing the street regardless, then this camera is recording that person, and not only recording it, but there's also image recognition and face recognition behind that, and it identifies the person that is crossing the street by the facial video data, and that is what's happening here. Displays this person and shames that person on a large screen next to the pedestrian crossing and say, hey, this person just crossed this street, even though there was a red light. This person just jaywalked. And if you look closely into the screen that I show here, it's not a person crossing, right? It's a bus driving by. Obviously, the pedestrian had red light. That's why the bus had green light, and the bus is driving by. And on the side of the bus, there's a person's face printed. And so the camera detected this face, identified the person, and in this case this is I think the CEO of the company that is now advertising with her face on that bus, and at that point she was in a different city, and she got a notification on her phone, hey, we just saw you crossing the street at red light in that other city. And she was obviously very surprised to hear that. Other cities have gone even further. They have not only have a big video wall where they then shame that person and send a notification to that person, but they deduct the fee for jaywalking immediately. Like there are cases where like you cross the street, your face gets identified due to, I mean, there are some regulations regarding opening bank accounts and whatnot in China, and using WeChat and WeChat Pay, which is super popular in China. And due to these regulations, the government is able to identify the WeChat and the WeChat Pay account of the person jaywalking, and is able to immediately, within seconds, deduct the fee for jaywalking if this machine learning, if this image recognition system identifies that person. And that is, as we can see here, where simply a bus was driving by with this face printed on. That is something where if it fails really badly. Like the impact that that this can have can be devastating. Like if we have machine learning in place that fails, as we can see here, that fails, but has the power to decide who is a criminal, or like who just committed a crime and who gets fined, and if we think this further, right, maybe who gets jailed, then we have a real problem, because we are accepting the fact that these decisions can be made faulty. I mean, always there are faulty decisions being made by humans in terms of when it comes to legal matters, but this one would have been obviously decided by a person. Okay, that's a bus, not a real person. Nobody needs to get fined, but the machine learning algorithm failed here, and in the larger extent, other systems will fail in the future when it comes to making these decisions, and that's where having this power given to the machine learning models is rather questionable. So I've said AI a lot, and I've said machine learning a lot. I think it is important to understand these terms, because they are a little bit hyped nowadays. They're very popular terms. I think it is important to have a common understanding, at least in this context for this talk. I would like to present my understanding so that we are on the same page there. And based on that, artificial intelligence is a term that is particularly popular nowadays. But there's a definition from the Oxford dictionaries that I really like. And if you type define artificial intelligence into Google, you'll get the same definition. And this definition reads: that artificial intelligence is the theory and development of computer systems able to perform tasks normally requiring human intelligence. And the important thing here to note is that there's no mentioning of a particular implementation or a particular technology or particular technique. It is the sole idea that whatever a computer system now does is considered to require human intelligence. And I'll give you an example, like a chess program. If you think of playing chess, you would usually assume that the person who can play chess has some level of human intelligence. Now, if you write a chess program, you could make this chess program relatively simple in terms of how it operates. You could simply look at the state of the chessboard and brute force all the possible moves that you can do and all the possible subsequent moves that you can do. And then at the end, just pick the set of moves that leads to a desired outcome, which is you winning the chess match. But from a software perspective, everything you've done is like maybe a couple of for loops, maybe a couple of if else. So there's nothing particularly fancy about this implementation. Yet it falls under this artificial intelligence terminology, and that is, I think, that is something that I hope more people would try to understand. That artificial intelligence itself doesn't particularly mean a certain approach or a certain technology. Where it becomes, at least from my perspective, particularly interesting is machine learning, because machine learning is a subset of artificial intelligence, and machine learning is special in the way that the algorithm that is used to then solve the problem is not defined by the software engineer. Not defined. It's not. It's not defined by ifs and elses and loops. It gets defined by the data that the machine learning model is trained with. Like you have this machine learning model, you put in certain data, and it adopts to that data and more or less tries to reproduce it. And when used in the future, it will then behave based on the data you fed in. If you feed in other data, the algorithm will behave differently. And that is something where, at least I think, that is something that is fundamentally different from the classical software engineering approaches. And then there are neural networks, which is a subset of machine learning. Relatively simply said, the algorithms that fall under the bucket of neural networks are algorithms designed based on biological brains. And then there's deep learning, something that has been particularly popular over the last couple of years, which is a subset of neural networks. And in fact, it is just neural networks with a lot of layers, a lot of nodes that are these neurons, basically. And right, and then there's data science, which uses some or all of these to get insights out of data. So I mentioned these neural networks. A typical representation is something that you have where you have an input layer, which is input data, and all these nodes based on the data that they have. If you talk about, we've talked about image recognition earlier. So if you have, I don't know, 1 million pixels, then you could have 1 million input pixels, and these input layer nodes do some kind of processing and then give an activation or give information to the next layer. And in this case, there are 3 hidden layers, and then there's all of these nodes do some kind of computation, and based on some kind of weight, and they sum up some of the input data. I'm not going to go deeper into how this actually works, but more or less the thing is that data is passed forward to multiple layers. And this is an example where it's 3 layers, and And the real life example nowadays have 50, 100, hundreds of layers sometimes. And not only like, what is this, like 10 nodes per layer, but like hundreds of nodes as well. And the thing to understand here, I've showed earlier how machine learning fails. And one of the reasons why machine learning fails is that it is, from a human perspective, it is too complex to understand why decisions were made in a certain way. This is a very simple example, but we can already see all these connections. There are so many connections between all of them. All of this is some kind of data flowing that at the end, based on input data, causes a certain output of this machine learning algorithm. And real life examples are thousands of times more complex. So it is virtually impossible for a human to comprehend why this set of image data or this set of input data caused this output. And that is one of the fundamental problems that exists in terms of machine learning. Is it is too complex to understand why things happen. It is not a simple, oh, I can debug by if else and then go into this function call and step my way through it through the stack trace. It's just too complex. And that is it's basically a black box behavior. And that is one of the issues that causes a lot of the failures that we see nowadays with machine learning systems in production. But that is only one issue. I talk about later how we can address that, but there is another big issue, and there's a nice example from 2011, where the city of Boston had a problem, which was they had too many potholes, and they wanted to change it. They wanted to fix that, and they did what everyone did in 2011 when they had a problem. They wrote an app. So they wrote this app called Street Bump. And the idea, I have to admit, the idea is pretty smart. This app, you would install it on a smartphone, and when you were driving in your car, you would put the smartphone on the passenger seat. And you would drive around, and whenever there would be a pothole, you would the smartphone would realize, through the accelerometer, would realize, look, there must have been something on the street. But then use the GPS coordinates and send to the backend servers, hey, this GPS coordinates had this bump, there must be a pothole. And then, therefore, the idea was that if everyone would use this app, the city of Boston would have a nice map and would know exactly where all the potholes were. Now, the problem is that then they looked at the data, and what the data showed was that only in the areas with a high cost of living, basically where the rich people were living, only in these areas were potholes being found. And if you rationally think about that, that doesn't make much sense, right? Why would potholes only happen in areas with a high cost of living? But the thing that the people forgot when they wrote this app, it was 2011 was a different time. Like nowadays, everyone has a smartphone. Every 5-year-old is watching TikTok videos, right? But 2011, smartphones were not as ubiquitous as they are nowadays. So the only people who could actually afford smartphones and therefore install this app were the people who had enough money to also live in the high cost of living areas. So, and that is, and the important thing to notice here is, I've given other examples where approaches failed. In this example, there was no machine learning involved. There was no AI in that way. It was simply that the data was wrong. The data was biased. The data was biased basically because the data was only produced by people living in high cost of living areas. And that is the important second factor that often makes systems based on machine learning or based on artificial intelligence fail nowadays. That the data is skewed in addition to the black box behavior of machine learning. Luckily, in 2011, the city of Boston found a solution to this, and I think the solution is as smart as the idea itself of this app. Instead of letting normal citizens of the city use the app, they installed this app on phones and put these phones into public buses that would drive around everywhere and into garbage trucks. So they then got a whole, they could cover the whole city independent of the income of the citizens of that particular region. So that is something that is that worked out after they had found the issue. But let me show you another example, and I've given this presentation a few times now at some conferences. Never in Turkey, but this is where it becomes interesting, because I go to Google Translate, and you might already know what I'm up for. But I show you some English text, and I translate it into Malay. And the interesting thing about Malay is that the pronouns are gender neutral. And this is where the comparison to the Turkish language also comes into play. But I use this for Malay because Google hasn't fixed the Malay version yet. But basically what I want to say is that she is a doctor, and he is a nurse. Obviously, we know there's nothing wrong with the female person being a doctor or a male person being a nurse, right? But look what happens if I now, this is the translated version into Malay. Look what happens if I now translate it back, the Malay version back to the English version. And remember, she is a doctor and he is a nurse. All of a sudden, it becomes he is a doctor and she is a nurse. So the English got translated into a gender-neutral language, and then I asked Google again to translate it back, and the gender-neutral then became gendered again in the English language, but basically had a different gender. And the reason for that, is the data that this machine learning model was trained with. Basically, the idea how these translation systems work is you let the machine learning model just read a lot of text that you have in multiple languages. And by reading these texts in Malay and in English and reading a lot of these texts, the model then learns how to translate the individual parts of these sentences. But the thing is that the data being used, and historically, being a doctor was historically a male job, and being a nurse, historically speaking, was a job for a female person, and that is represented in those texts that were used to train these models. And based on that, now this model translates using this social bias that was in the text and puts that into this translation. Now that is, and I mentioned that if we do this now, I think we can try to do this now in Turkish, and we can see what happens there. I'm not going to try to translate that. So this is particularly interesting. So for some reason now this is she is a nurse and she is a doctor. The nurse changed, the doctor did not. There's something very interesting that I have seen Google done. I mentioned, and you probably know that better than I do. But there was this became very popular a couple of years ago, and Google reacted in a way that they realized, okay, gender neutral pronouns in a language, and then they provided multiple translations. I've a screenshot here. So I have not figured out. Sometimes Google Translate is translating it and it's showing me these. Sometimes it is using the assumed gender based on the training data. Anyway, the point that I try to make here is that the historical data that is in the that the machine learning model was trained with represents itself in these translations. And maybe you also remember this Tay. Tay was something that Microsoft tried a couple of years ago. Basically, a Twitter bot. I think it was also on other platforms. But the idea was to have a greenfield machine learning model which knows about language a little bit, and then the idea was that it learns to speak sentences by observing behavior of humans on the internet. Now, if I go on the internet and look how humans behave, I'm relatively convinced that it is a bad idea to train anything based on that behavior, how humans do that on the internet. But Microsoft tried it anyway, and surprisingly or unsurprisingly, the outcome was a horrible racist Twitter bot that they had created. They are absolutely horrible examples. Obviously, people figured out it's a machine learning model, and they did it on purpose and tried to feed in horrible ideas into this machine. But the point is that it worked, and that the data that was trained with ended up then defining this communication spot. And I think the last one, this example is particularly fitting, where Tay has to admit that it only learns from the people tweeting towards her or tweeting to her, and if she turns out to be stupid, then it is because the people she learns from are stupid, right? And that was, I mean, that is something. I mean, that was. I would almost say that was to be expected, but it could be turned off within a day, so the damage wasn't that big. Now, where the damage becomes like exceptionally high is in the system called COMPASS that is used in the US, which is, I mean, it stands for Correctional Offender Management Profiling for Alternative Sanctions. Basically, what it is you commit a crime, then you fill out a form with like 200 fields or something, some information about you, and that gets passed into a machine, and the machine then predicts how likely it is that you re-offend. So you committed a crime, and then this machine says, based on the questionnaire, how likely is it that you commit another crime in the next couple of years? And this information then is used by in court by judges to determine how high your bail is, so how much money you need to pay to be free, or even used to determine how long you have to go to jail. And ProPublica did an analysis of this, and the outcome was horrifying. So they are basically, I mean, if everything is correct, then the model worked fine, right? But if we look at the times where it failed, there's a very terrifying trend in this data. And we can separate, or ProPublica separated between white and African Americans. And they looked at the people who were labeled a higher risk, where the machine learning model said, hey, where this COMPASS system said, this person is likely to reoffend, is likely to commit a crime again, but then the person actually did not, right? So they were labeled a higher risk, and that was only for 23% of the white people the case, but for almost 45% of the African Americans. And the same thing, like the same failure, but the other way around, where people who actually committed a crime again, but the system labeled them a low risk, that was almost 50% for the white people, and only about 28 for the African Americans. So this model or this system that is still being used today and that determines how long people go to jail is highly racist towards African Americans, right? And the questionnaire that is being used doesn't even ask for skin color or the ethnic background. The information that is being used is information about where people live, the neighborhoods, some of the parents, and this data is then used, and in this way has a very high bias, and the bias causes people to go to jail longer than others, right? And I think that is an example where the failure is horrifying. And there are more examples. Autonomous driving will that's a prediction, but over the next couple of decades, in 20, 30 years, autonomous driving will probably take over a lot of the driving that we have nowadays. And a lot of these autonomous driving cars work in a similar way, that there are lots of sensors around, LiDAR, like laser, right? And we have infrared sensors, and a lot of them are cameras. In fact, there's one system that only relies on cameras. And what these cameras are doing, there's a machine learning model. It does object recognition. It recognizes, hey, there's a red light. It recognizes, hey, there's a stop sign. It recognizes where the lanes of the road are, and it also recognizes pedestrians. And there's this study that finds that, and identifying pedestrians is, I would argue, is an essential part concerning the safety of autonomous driving. And there's a study that finds if you are a dark-skinned pedestrian, you are less likely to be identified as such. And the result is obvious, that the autonomous driving car, if there are enough of them and if there are enough encounters, will eventually kill people, because it does not identify people as pedestrians. And the rate for what that means that the rate for dark-skinned pedestrians to be identified is lower, means that they are more likely to get killed. And I think that is again the data that was used to train this was probably lacking a diverse set of image data. It was probably mostly trained on pedestrians, on light-skinned pedestrians, and therefore the model simply is less successful identifying dark-skinned pedestrians. So that is another quite impactful and horrifying example where the data we use to train machine learning models has horrifying outcomes. And I remember being a kid and I wanted to do something, and my mom said no, and I said, oh, the other kids are doing it, and my mom still said no, because it doesn't matter, right? Machine learning model is this mother that says, okay, if everyone else does it, go ahead, do it. Right, so in summary, I've told you now that basically the world is on fire. Machine learning horribly fails. It gets widespread deployed nowadays. Is there anything we can do? And the good thing is we can. And there's one thing that in the machine learning or in the industry as a whole, that explainability of machine learning models become an important factor. Actually being able to understand why the machine learning model reacted in a certain way, had a particular outcome, why this happened. Basically working against this black box behavior where you don't know why things happen. That has become a more popular topic in the industry nowadays, and people are paying attention and building models that have a better explainability. One example is, for example, for image data. You can see here on the bottom right, there's some kind of image recognition deep learning model, and it uses convolution, or it's a convolutional neural network in that case. And there is this method, which is a deconvolutioning, which basically turns these activations of those neurons in those layers back into images. So you can see on the very bottom, the input layers is just random pixels, but then the further the data gets piped through the network, the more precise do the predictions get. Like the next layer identifies edges, and then there's at some point you identify facial features and all of that. So that is one example where that works. Basically, what we need to do, we need to move away from the typical standard ML where you just have data stored in a model and then you hope it works, into a system where we have human feedback and inspection and add interpretability to this. Another tool is Line, which helps you interpret these models, and that works in a fantastic but also simple way. That it uses data to see what the prediction is, and then it uses the same data but removes certain elements and see how close the prediction still resembles the original prediction. Like we see here, there's an image of a frog, and the prediction is, hey, it's a tree frog. And then we remove parts of the image and see how what the prediction is. And in this case, you can see on the top what is relevant for the machine learning model to identify this as a frog. And you can see basically on the bottom right, the most important features is like the frog face and that the frog mouth for the system to identify it as a frog. Basically, if you the very picture in the middle, if you remove this and you keep some of the background and the prediction is very far off from the original prediction, you know all of the things that I still have here are not relevant. Right, and that is something that helps us, or it helps people in the industry identify what is actually happening and what is actually the important data that is being used here. Another thing is simply having more diverse teams, like the software, and maybe that would be helpful in all software development categories, but particularly in terms of machine learning. Have a diverse set of team members, have a diverse set of software testers who actually test a broader range of scenarios. I would argue that the example with the autonomous driving cars, the reason why dark-skinned pedestrians, it's very likely that the data was used was mostly light-skinned pedestrians. And the reason for that is probably because most of the developers fit into this category. If there would have been a diverse set of developers, the outcome would have been probably a little bit different. Another thing that I can recommend is using the data ethics canvas that got published by the Open Data Institute, and is basically a guideline when you start working with a lot of data on what kind of questions you need to ask yourself. Are you saying that? What are the limitations? And a couple of other things, how you're sharing that data with. Another example is another thing that you can do is remove data. Do you need to know the skin color if you are working on, I don't know, if you're working in a system that doesn't need to know that? If not, throw it out. It's not as easy because you have quasi-identifiers where you can, just like the example with the compass system where the skin color never was mentioned, but they still developed a bias against African Americans. So there is data where you can derive this from. But I think in general, the idea is if you strictly don't need that, then don't use this data in training your model. Right, and then there are some more tools like this one, which is released by Google Facets, where you can just throw in your data set and it visualizes it really nicely, and you can immediately see, oh, look, there's only 20% of my users or of my data points are actually female users. So I have highly underrepresented the female gender, and therefore I need to adjust my data set a little bit. Right. What if is a similar tool that lets you understand what machine learning and how the data that you are using with that works. That being said, thank you very much for your attention, and let me know if you have any questions. I mean, I can. I'm just around here in this chat, so you can just type some questions. Other than that, thank you all for your attention.